Hello and welcome back. In this class, we'll be talking about imperfection in crystals. We'll see what does that means. What is imperfection in crystals? Well, if we have a look at a crystalline structure, as you can see over here, a crystalline structure has got a very regular pattern. You will see that every cation is surrounded by anions and every anion is surrounded by cations. So this is a regular pattern in a crystal where cations and anions, they are surrounding each other. So they are attracting each other, and as a result of that, there is prominent attraction due to which a crystal is stable. But many a time it happens that this arrangement get disturbed. There is some randomness in this crystalline structure. That randomness can be of two types. That can be either line imperfection or point imperfection. Line imperfection means what? You can see, as you can see, this is a plane where you got cation, anion, cation, anion, cation, anion. This again is a plane where you have got anion, cation. If somehow or the other these planes they move over each other, then a situation can come. Initially, what was there? A cation was surrounded by an anion. But if the layer moves a bit, it may happen that in front of a cation you will have another cation, in front of an anion you will have another anion. This will lead to repulsion, and as a result of that, the crystal will break from that particular plane. That is known as line imperfection. So line imperfection is not there in your syllabus. Today we'll be talking about point imperfection. Point imperfection means what? You have got a regular pattern like cation, anion, cation, anion, cation, anion. So when you are moving cation, anion, cation, it may happen that cation is not there. Or cation, anion, cation, anion, cation, anion is not there. Either a cation or an anion is found missing. Such an imperfection is known as point imperfection. Point imperfection is also to an extent responsible for destabilizing a crystal, but it is also responsible to increase the electrical conductivity of the crystal. So we'll see these imperfections. Well, point imperfection can be basically divided into two parts. That is vacancy and interstitial. Vacancy imperfection and interstitial imperfection. If I talk about vacancy imperfection, what happens in vacancy imperfection? It may happen that you got a regular arrangement like here in this case, you got cation, anion, cation. It may happen that a cation is found missing from its respective position. So you got a vacancy over there. You'll see a vacancy, a vacant place over there. This is vacancy. Not only a cation, it may also happen that an anion is found missing from its respective position. So whenever a situation is like this, where a cation or an anion is found missing from the respective position, that will lead to the formation of voids, empty spaces. This is known as vacancy imperfection. These empty spaces, they are always responsible for higher electrical conductivity. So this is vacancy. Vacancy imperfection can occur in any type of a crystal. In all crystals, vacancy imperfection can occur. So this is what a vacancy imperfection is. Now we'll see interstitial imperfection. Well, in interstitial imperfection, only a cation is found missing. But instead of moving out of the crystal, the cation occupies an interstitial site somewhere. Like it is here only. It is not moving out of the crystal. In vacancy imperfection, the cation and anion, they were moving out of the crystal. Same number of cation and anion, they were found missing. For example, if I talk about sodium chloride, say I have got 100 sodium ion and 100 chloride ion. That's why the formula was NaCl. Now out of 100 Na positive, 10 Na positive they are missing. So I have 90 Na positive. And same number of chloride are also missing. So I have 90 Cl negative. Again the formula is NaCl. So formula is not changing. That means same number of cation and same number of anions, they are found missing. Such an imperfection is vacancy. In interstitial, again the formula is not changing, but the ions, they are not moving out of the crystal. The ion, like the cation, is found missing, and instead of moving out of the crystal, it is occupying an interstitial site. As you can see over here, it is occupying an interstitial site. Such an imperfection is interstitial imperfection. Interstitial imperfection cannot occur in all type of crystals. For example, if I talk about sodium chloride cannot show me interstitial imperfection. Please do remember this thing that any crystal which has got a larger cation cannot exhibit interstitial imperfection. Because what you are noticing here, suppose this is one of the anion, this is another anion, and this is the third anion. Between these anions, you will see this vacant space. The cation is occupying this vacant space. This is what is happening here. But in case the cation is larger, like S block element, sodium, potassium, rubidium, cesium, magnesium, these larger cations, they cannot occupy this small space. So S block elements, any compound of S block element cannot show interstitial imperfection because these cations, they are larger and they cannot be fitted in the interstitial void. So NaCl cannot show interstitial imperfection. So these broadly, these are the two type of imperfections which we'll talk about. So they can further be classified as stoichiometric and non-stoichiometric. Stoichiometric imperfections are those in which the molecular formula of the compound remains same. The molecular formula of the compound does not changes. This imperfection is further divided into two, right? The first one is Schottky and Frenkel. So first we'll see Schottky. What is Schottky imperfection? Well, very correctly, Schottky is vacancy imperfection. It is vacancy imperfection, what we have done. This type of imperfection generally occurs in crystals which have their high coordination number. And we can say that all type of crystals, they are capable of exhibiting this type of vacancy, this type of imperfection, where same number of cations and anions, they are found missing. So in Schottky imperfection, same number of cations and anions are found missing from the crystal. So the molecular formula remains same. But if we talk about Schottky imperfection, it always results in decrease in density. As you can see over here, the number of ion per unit volume will decrease, so the density will decrease. All type of crystals can exhibit this type of imperfection. So this is what Schottky imperfection is. It will lead to a decrease in density. Next we'll talk about Frenkel imperfection. Well, Frenkel is very correctly interstitial imperfection. In this type of imperfection, a cation is found missing from its respective place, but instead of moving out of the crystal, the cation occupies an interstitial site. So instead of moving out of the crystal, the cation occupies interstitial site. So number of ion per unit volume will remain same because the ion is not moving out of the crystal. That's why density remains same. and molecular formula of the compound also remains same. Molecular formula of the compound will also remain same. So these are two different type of stoichiometric imperfections in which the molecular formula of the compound will remain same. In Schottky, the density will decrease, whereas in Frenkel, the density will remain same. All crystals can exhibit Schottky imperfection. Any crystal which has got a larger cation cannot exhibit Frenkel imperfection because larger cations, they cannot be fitted into voids, smaller voids. After this, we'll move on to the non-stoichiometric. When I'm saying non-stoichiometric, that means the molecular formula of the compound will change. Now suppose I've got a compound which has got a molecular formula Mx type, where M is a metal, M positive is a metal and X negative is a non-metal. So the change in formula can be either the cation can be more or the anion can be more. So non-stoichiometric can be divided into two types. That is, first one is metal excess imperfection. This is generally induced imperfection. Generally, it does not happen on its own. We carry it out. So this can be means stated as an induced imperfection. I'll give you example for that. Now suppose this crystal I have got is of sodium chloride. We'll see this crystal. This is a regular crystal of sodium chloride. Now what I am doing, these are the boundaries of this crystal. This is a crystal of sodium chloride I have got. I am putting this crystal in the vapors of sodium. These are the vapors of sodium. So when I am putting this crystal in the vapors of sodium, the sodium atoms will get adsorbed on the surface of this crystal. So they are getting attached at the surface of the crystal. You are getting a crystal like this. Now what happens, since the concentration of sodium ions or sodium atom at the surface is more, because sodium has got adsorbed on the surface of the crystal, so the concentration of sodium is more at the surface of the crystal, due to which some of the chloride ions, they will move out. Suppose this chloride ion is moving out to combine with this sodium. When the chloride ion has moved out, a definite number of chloride ions, they are moving out. It means what in this situation you are having more number of Na positive than the number of Cl negative. That means the molecular formula has changed. Initially say you have got 100 Na positive and 100 Cl negative. Now say 10 Cl negative, they have moved out of the crystal to combine with sodium. You have got 100 Na positive but you have got 90 Cl negative. So the molecular formula is changing. Here you are seeing metal excess imperfection. More number of metal ions they are there. Now what happens in this? When the chloride ion is combining with sodium, you know very well that chloride does not combine with sodium, it combines with Na positive. So in this process, when a chloride is combining with sodium, sodium is losing an electron. That electron diffuses into the crystal, that moves into the crystal. And it occupies the position from where the chloride ion has moved. So this is an electron I have got. From there, a chloride has moved out, but in that place, on that void, an electron has come. As a result of that, what is happening? Na positive is more as compared to Cl negative. You have more number of cation as compared to the number of anion, but the charge is same. Suppose you have got 100 positive charge, Na positive. You got 100 negative. Out of those 100 negative, 90 is Cl negative and 10 is the electrons which have diffused into the crystal. So charge remains same, the charge is balanced. Now what this electron does, this electron is very essential for this crystal. It improves the electrical conductivity. Moreover, this electron is also responsible for the coloration of the crystal. Actually what happens when white light, it strikes on this electron, it gets excited and it moves out of its position. Then again, due to the attraction of these cations, it moves back. And this process, it keeps on happening. So what this electron does, it absorbs light of a particular frequency from white light, it moves out, then comes back, then again absorb light of a particular frequency from white light, moves out. In this process, it absorbs light of a particular frequency, keeps on moving and reflect rest of the light. Now, as a result of that, the crystal will appear colored. So, as a result of that, if you put a sodium chloride crystal in the vapors of sodium, they acquire slightly yellow color. So, sodium chloride crystal turns pale yellow in the vapors of sodium. Now, since this electron is responsible for the coloration of the crystal, we call it Farb center. Farb means color in German language. So, Farb center electron or F center electron. Again, when you put a crystal of sodium chloride in the vapors of sodium, the sodium atoms will get adsorbed on the surface of the crystal, due to which some of the chloride ions they'll move out to combine with sodium, and in this process sodium will lose some electron. Those electrons they will diffuse into the crystal, they will occupy the vacancy which is created by the loss of chloride ion. Although the number of cation is more than the number of anion, but the number of negative charge is equal to the number of positive charge. These electrons, when white light falls on these electrons, they get excited by absorbing light of a particular frequency from white light, thus reflecting rest of the light. And as a result of that, the crystal acquires color. Well, sodium chloride, if I talk about sodium chloride, as I have told you here, sodium chloride turns pale yellow in the vapors of sodium due to F center electron. Lithium chloride turns pink in the vapors of lithium, and potassium bromide turns violet in the vapors of potassium. So all these crystals, when they are placed in the vapors of their corresponding metals, they acquire color due to the presence of F center or Farb center electron. I give you one more example. Suppose I have got zinc oxide, ZnO. If I heat it, it also becomes, this is white color crystal. If I heat it, it will acquire slightly yellow color. And in that, now say the ratio means the ratio which is metal to non-metal. Oxygen now is lesser. Initially you have 1:1 ratio. Now say it has got 1:0.98. 0.98, 0.96, 0.99, 0.97, but it is not 1:1 ratio. So here also it is acquiring color because of F center electron. Actually what is happening when you are heating zinc oxide, it is becoming ZnO, say it is 0.98, and it is losing some O2 negative ion. This 2 moles of O2 negative ion will get converted to O2, losing 4 electrons, and these electrons they will again occupy interstitial site. They will behave like F center electron and they are responsible for coloration. So this is how zinc oxide also becomes pale yellow. So this is metal excess imperfection. Next we'll talk about metal deficiency. Second is metal deficiency. Metal deficiency imperfection. We'll see what metal deficiency imperfection is. When I'm saying metal deficiency imperfection, now say here I've got negative. This crystal is not sodium chloride in this case. Suppose this crystal is CuCl, cuprous chloride. So there is no sodium in this case. This is altogether a different crystal. This is a cuprous chloride crystal. In this case, what is happening? Some of the chloride ions, some of the Cu positive ions, they are moving out. Some of the cations, they are found missing from their respective position. Suppose a cation is found missing from this position, another cation is found missing from this position. So as a result of that, why one more thing which comes to our mind, why these cations they are missing from their respective position? You might be thinking that actually what happens in a crystal there is a perfect balance. These cations and anions they are electrically charged and they vibrate on their mean position. Suppose a cation is vibrating, anions are surrounding that cation. So there is a prominent force of attraction due to which it is held on its mean position. But many a time it happens that some of the cation or anion they have got very high energy, so they are vibrating very vigorously, and the vigor is so large that these anions or cations they are no longer capable of holding that ion between them. So suppose a cation is vibrating very vigorously and anions they cannot hold it, the cation will leave its position and it will move out of the crystal. So suppose from here some of the cations they are found missing. That means the number of cation is lesser than the number of anion. So in this case, if we talk about this formula, initially the formula was say CuCl, but now the formula initially it was CuCl, but now say the formula has become Cu.98 is to Cl. You have lesser number of cation. This is metal deficiency. But actually, what happens in this type of imperfection? Although the number of cation is lesser than the number of anion, but the positive charge is not lesser than the negative charge. Here you have Cu positive and Cl negative. But in this one, what is happening? You have some of Cu positive, but some other Cu positive are moving to their higher oxidation state, that is Cu2 positive, so that the charge will remain balanced. Again, some of the Cu positive ions they are found missing, they are out of the crystal. In order to maintain electrical neutrality, some other Cu positive they are moving on to Cu2 positive. They are losing electron, they are moving on to the higher oxidation state, so that although the number of cation is lesser than the number of anion, but the net positive charge becomes equal to the net negative charge. So if you talk about this, you are definitely going to have some of Cu2 positive cuprous and cupric ions in this. In this type of imperfection, we can say a limitation is there, that only those crystals in which metal can exhibit more than one oxidation state can show this type of imperfection. Not all. If I talk about sodium chloride, whether sodium chloride will be able to show this type of imperfection? No, because sodium exhibits only one oxidation state and that is +1. Any metal which can exhibit more than one oxidation state can show this type of imperfection. So as I have shown you, like cuprous and cupric, in that this type of imperfection can occur. I can talk about say Ni nickel oxide, because nickel exists in two oxidation state, Ni2 positive and Ni3 positive. I give you one example. This is given as a question in your textbook. Suppose I have nickel oxide. Now after imperfection, it is becoming Ni.98 is to O. Now the question is asked, what is the fraction of Ni2 positive and Ni3 positive in this crystal? Well, I don't know how many among them are Ni2 positive. So let Ni2 positive is X. So Ni3 positive is 98 minus X. Now if I talk about their net positive charge, I can see the net positive charge has to be equal to that of oxygen. If Ni total number of nickel atoms is 98, that means oxygen is 100. Because I'm multiplying this side, the nickel side I'm multiplying by 100, so oxygen side should also be multiplied by 100. So that means what? Say 100 oxygen, one oxygen has got 2 negative charge. That means 100 oxygen will have 200 negative charge. That means what? 98 nickel should have 200 positive charge. No matter whether they are 2 positive or 3 positive, but their charge has to be equal to that of oxygen. That means what? 2 into X is the total charge because of 2 positive nickel. And 3 into 98 minus X is the total charge because of 3 positive nickel. See, the number of 3 positive nickel is 98 minus X. and one nickel has got 3 positive charge. So these ions will have total positive charge, that is 3 into 98 minus x. One nickel atom has got 2 positive charge, so the total positive charge is x into 2, because the number of 2 positive nickel is x. And that total charge is equal to 200 positive. From here you can easily calculate the value of x, that is the number of Ni2 positive. If you subtract that from 98, you will get the value of Ni3 positive. So this is metal deficiency. So metal deficiency imperfection can be exhibited only by crystals in which metal can exhibit more than one oxidation state. After this, I'll tell you something about another induced imperfection. Induced imperfection, where I'll talk about some of the semiconductors. See, by now this is quite clear to you that imperfections, although they destabilize a crystal to a bed, but they're definitely going to create some empty spaces or some extra ions somewhere which are responsible for greater electrical conduction of the crystal. So we'll see induced imperfection, because by doing so we can increase the electrical conduction, and this imperfection is particularly useful in increasing the electrical conduction of semiconductors. Now suppose here I have a crystal of silicon. Silicon belongs to carbon family. So like carbon, it has got tetra covalency. It is forming 4 bonds. This is a 14th group element. So here again you'll see silicon attached to 4 other silicons. One more row of silicon, you will see silicon here attached to all silicon atoms. Well, silicon as such is semiconductor and has got a very limited electrical conduction, not a very good conductor. But if I put some impurity into this, if I induce some imperfection into this, then its electrical conduction increases. We have 2 different type of semiconductors based on that. First I'll tell you 14-13 group. That means what? In 14th group, that is in silicon, I am putting impurity of 13th group. 13th group impurity, what I am putting? I can put, say 13th group elements are boron, aluminum, gallium, indium, all of this, thallium, I can put this. Suppose I am putting gallium, which commonly forms 3 bonds, gallium or boron. Okay, we'll do one thing, we'll take boron. So, here in this case, I am replacing one of the silicon atom I'm replacing the silicon atom by a boron atom. Now suppose here in this case you got a boron. Boron in valence shell has got 3 electrons, so it is forming 3 bonds. But you will say there is a vacancy. This is a hole you have got, empty space. We call it hole. Initially when there was silicon, there was no hole. All electrons, they were bonded together. They were stable, they were not conducting electricity, or they were conducting electricity to a limited extent. But now you got a hole. So what the situation is, when you connect one side, this is the another side. When you are connecting one side, say you have got a positive terminal here and you have got a negative terminal here. The electrons from this side will jump into the hole. So the hole will come here. Then electrons will jump here. Then hole will come here. So likewise the electrons, they will start moving from negative to the positive, and the hole will start traveling in the opposite direction. As a result of that, the electrical conduction will increase. Such type of a semiconductor is known as P-type semiconductor, or we can say positive type, where hole is a charge carrier. So you can see that hole is conducting electricity. So whenever you are doping means we are putting impurity. So doping always means adding impurity. So whenever you are doping a 14th group element with a 13th group element, definitely you are going to get some vacant spaces. Those empty spaces, they are known as holes. When you connect such a crystal with 2 terminals, the electrons, they'll start moving from negative to positive, and the hole will start traveling from positive to negative. So it will show some electrical conduction. Such a type of semiconductor is p-type semiconductor. Now I'll tell you another situation. This is p-type semiconductor. We'll see another situation. In this, there's no boron. In this situation, again I've got a silicon here, same crystal, silicon bond. Now I am adding, in 14th group, I am adding an impurity of 15th group. 15th group elements are what? 15th group elements are, say, nitrogen, phosphorus, arsenic, antimony, bismuth. Suppose I am adding arsenic. So first I have to remove a silicon atom. So here I have got arsenic as an impurity. Since it belongs to 15th group, that means in the valence shell it has got 5 electrons. With 4 electrons it is forming bond, and here you will see an extra electron. So you got an extra electron. Now since extra electron has come into the crystal, this extra electron is responsible for increased electrical conduction. You got some free electron inside the crystal. So when you connect it with the terminals, electrons from the negative terminal, they'll start coming into the crystal, and these free electrons, they'll also start traveling under the influence of electric field. And since these free electrons, they are moving in the crystal, they'll show some electrical conduction. That means the electrical conduction of the crystal will get increased. Such type of semiconductor is known as N-type or negative type. In N-type semiconductor, free electrons are charge carrier. So we have two different type of semiconductors, that is N-type and P-type. These semiconductors, they are largely used nowadays in transistors, in diodes. Diodes, they are used as rectifiers, which are basically used to convert alternating current to direct current. If we talk about transistors, see, I've got N-type semiconductor, then I'll put a P-type semiconductor, then again I'll put a N-type semiconductor. That means the P-type semiconductor is sandwiched between two N-type semiconductors. So I have N-P-N transistor. Likewise, if I got a P-type semiconductor, then I have N-type, then again I have P-type. This is PNP semiconductors. The PNP transistor. Such transistors, they are used to detect and amplify radio signals and audio signals. So in amplifiers, they are quite widely used. And diode, as I've told you, they are used as rectifiers. So in today's class, we have talked about imperfection in crystals. In that we can see an interstitial, and then stoichiometric, non-stoichiometric. In stoichiometric, we did Schottky and Frenkel. In non-stoichiometric, metal excess, metal deficiency. And then induced imperfection. In that we talked about doping. And after doping, see again, doping is what? Addition of an impurity into the crystal is doping. And by adding that impurity, we not only add some imperfection in the crystal, but we also increase its electrical conduction. We talked about N-type and N-type and P-type semiconductors. Here I would like to add one more thing, which I skipped in the first lecture also, and here also. Let me tell you one thing. Say you got a sodium chloride crystal, or we'll move to the initial crystalline structure which I have drawn. I'll show you there. Suppose this is a sodium chloride type crystal. Now in this case, it is NaCl. In this NaCl, what you will see that if you talk about one Na positive ion, you'll see this Na positive is surrounded by a chloride over here. So this is one of the chloride, second chloride, third chloride, fourth chloride. One of the chloride is towards me, outside the plane of the paper. It is outside the plane of the paper, one of the chloride there. another chloride on the back of the plane of the paper. So one of the sodium ion is surrounded by 6 chloride ion. Likewise, one chloride ion is surrounded by 6 Na positive ion. So in case of NaCl, the coordination number is 6 is to 6. So this is what a coordination number is. This is what I wanted to tell you. What is a coordination number? A coordination number is the number of oppositely charged ions surrounding a particular ion. Or we can say if it is a neutral crystal, metallic crystal, it is the number of atoms, ions or molecules surrounding a particular molecule. So that is what a coordination number is. This is what we were scheduled for today's class. So we have talked about imperfections. In your next class, I'll be talking about the band model of conductor, semiconductor and insulator, and also about the magnetic property of crystals like paramagnetic, diamagnetic, ferromagnetic, ferri, antiferro. This is what we are scheduled for the next lecture. But again, one request to you, please do subscribe this channel to get all the notifications on time, and please do press the bell icon also. Thanks for joining. Thank you very much.